Hello everyone. So today we are going to discuss about optical sources. In the last class we had discussed about lighting, basics of lighting systems like radiometry, photometry and colorimetry. So today now we are going to discuss about optical sources which will be used in optical wireless communication. So the typical optical sources which we will consider are LED and lasers. So let us now understand the typical requirements of an optical source, whether it is for optical fiber communication or it is for optical wireless communication. So first, that the size should be very small. It should be as small as possible. The second is you want that power output, the optical power output which is coming from the source is proportional to electrical current, because ultimately I'm going to modulate my electrical signal. So I want my power output to be proportional to electrical current or electrical input. It should have high electro to optical conversion efficiency. That means whatever my electrical power is, it should give corresponding optical power. So you should have that conversion rate between electrical power to optical power should be high. Electrical power to optical power. The spectral width, that is delta lambda, should be small. What I mean by spectral width? Spectral width is, if the light is emitting at a single color, then it will have a fixed lambda. Suppose this is my lambda and this is a single wavelength source. So this is a lambda 0. So we will say that light is emitting at wavelength lambda naught. But in normal practice, this lambda 0 is not a single wavelength. So it has some spread around lambda naught. So this spread is called as a spectral width. So we want this delta lambda to be as small as possible, because if the light has many colors, in communication this could be a problem, because each wavelength will travel in the medium with different speeds, and when they travel with different speeds, they arrive at the receiver at different times, and at different times meaning there will be a dispersion in the pulses, or the pulses will spread. So suppose if you launch a pulse like this, if your delta lambda is high after say 20 kilometers or 30 kilometers in optical fiber, for example, this pulse will become something like this. So if there is a dispersion in time, then it will start interfering with next pulses. So it will result into a limited data rate, or it will result into something called which is called as inter-symbol interference. So we want this delta lambda to be very small. We want high bandwidth capability, which means I should be able to modulate the source at high speed. It should not be limited to, the wavelength, the modulation bandwidth should not be kilohertz or even megahertz. I should be able to modulate the source at high data rate, or it should have high modulation bandwidth of the order of few gigabits per second. So these sources should have high modulation capability. The sources should be energy efficient. The kind of power which we apply to LED and laser should be small, and it should give you adequate optical output. So the sources are expected to be energy efficient, and of course it should be low cost and should have long life. So let us first understand the basic principle of a LED. So LED is basically a PN junction diode which is forward biased. This is P, this is N, and this is the depletion region, and this is forward biased. So what happens in a LED when you forward bias it? Some of the electrons from the lower state, they go to the higher state, and from that state they fall onto the lower state and they release energy, and this energy is in the form of photons. So this is your lower energy level, this is your high energy, let's say E1, this is E2. So some of the electrons which are here, they will go up when the current is supplied to the device by giving this forward bias, and these electrons come at the higher level and then they fall down, and so this may result into two types of radiations. One is a radiative recombination, and another is this result into light output, and another could be a non-radiative, which may not result or which will not result into any light output, non-radiative recombination. So this is the basic principle of LED, and the photodiodes are of two types: direct band gap and indirect band gap. So for direct band gap, the light which is emitted from a PN junction is given by Hc. H is Planck's constant, C is velocity of light, and Eg is the band gap energy. So the lambda which is emitted is given by Hc by Eg. And if I put the value of Planck's constant and I also put the value of C here, and then the lambda is actually 1.24 divided by Eg, and this Eg is in electron volts, so the units are important here. So you have to put the value of Eg in electron volts, and then wavelength which you get using this expression will be in micrometer. So the lambda which is emitted is equal to 1.24 divided by Eg in electron volts, and the wavelength is in terms of micrometer. So if I take different material, for example, if I take silicon, the band gap energy is 1.12, it will give you a different wavelength. If I use gallium arsenide, the band gap energy is 1.43 electron volts, and for germanium it is 0.67. For indium phosphide it is 1.35, and then you can have a different combination of gallium and aluminum, and then you can get different value of band gap energy. So basically you can change the doping. So this is GAX, or rather it will be ALX, because you're adding aluminum as a doping, ALX, GA1 minus X into AS. So you can change the value of this X, and then you can get different band gap energy. And when you change the band gap energy, essentially you are changing the wavelength of emission. So for example, in this case, GA is GA 0.97, aluminum 0.03, and AS. So this gives a band gap energy of 1.51. So similarly, if you plot, for example, have different levels of X, this is say aluminum mole fraction, and this is the wavelength of emission. So this will be something like this. So this is starting point 0.3, and this could be 0.8. So by changing this value of X, that is the doping concentration of aluminum in the material, you can get different value of band gap energy and hence lambda. So you can make your lambda as per your choice, because as we know, there are certain wavelengths which are useful for communication. For example, the wavelength which are around 850 nanometer or 1310 nanometer or 1550 nanometer, they are all good for communication. using optical fiber where they have low loss. So you can generate a wavelength of your choice by changing this value of x. Of course, this gives you this is 1.3. I'm sorry about this. Is 1.3 and 1.8 micrometers. So you can basically get a wavelength ranging from 1.3 to 1.8 by changing the value of x. So this is another example where you have EG actually is represented in terms of 1.4 plus 1.2 into x plus 0.2 into x square. So this is a generic equation for EG, and depending upon what value of x you choose, you can find out this EG, and corresponding to EG, there will be a wavelength of emission. So now we will study the two important things of a source, which one of them, as I mentioned, is the spectral width, which we call as delta lambda, and the other one is the modulation capability of the device, modulation bandwidth of the device. So these are the two important aspects of any optical source. So first we will study the spectral width part. So let us consider a PN junction of, so this is, for example, your valence band, then this is your, conduction band. So there are electrons here. There will be some holes when you supply the current. So there will be some holes. And here, there are different states. So the electron is not limited to one energy line, but it has some distribution here. Similarly, the holes are distributed here. And this is the radiative recombination part. And similarly, you have the another part which is non-radiative recombination. So both are happening in the semiconductor. And this is valence band. So this will energy E1 and this E2. And E2 is not a sharp line. It can be, is a broad line for these energy states. So let us find out what is the probability of photon generation. So it is proportional to Ne2 into Pe1. Ne2 means the probability of electrons in the conduction band. So this is probability of electrons in the conduction band. And Pe1 is the probability of holes in the valence band. So the probability of photon generation will be, you should have electrons and holes. When they combine, they either give you radiative recombination or non-radiative. So for simplicity, we will assume that all electron hole pairs, they result into some photon generation. So there is no non-radiative recombination. So this probability of photon generation is given by this. And there's an expression for Ne2 and Pe1 which takes into account the Fermi level also, but that Fermi level part is constant. So I am absorbing that constant into that proportionality sign, and this is proportional to e raised to minus E2 minus E1 divided by kT. K is the Boltzmann constant and T is the temperature. So this is the probability of photon generation. And the total photons, if I see here, and I'm assuming that all the electron hole pairs are combining radiatively, they are emitting photons. So basically this will be an integration of, because this electron may combine with this hole, for example, this electron may combine with the different hole. Similarly, there are other holes also. So basically I need to integrate all possible combining of these electron and hole pairs. So I will be integrating this from EC to EPH, and EPH is the photon energy which is emitted. which is given by between this point and this point. So this is EPH, and this EPH is actually varying for different pairs. So this total photon, and it is integrated from EC to EV plus EPH. And if I simplify this integration, this becomes EV plus EPH minus EC into e raised to the minus EPH by KT. And if I multiply by e raised to power plus EG by KT and E minus EG by KT, I somehow simplify this expression. So this is the constant. This part is a constant, this part. So if you see this part, this is nothing but, x into E minus x kind of form. So if I plot this function, then this will give me something like this. So this is, for example, EPH. Now I'm plotting this, and this is the power, because this is the photon generated. So this is the optical power. This will give me something like this. This is the EG point where this power is 0. EPH is equal to EG is 0, and it has a maximum at EG plus KT. And if I see this distance or this width, this is nothing but 2 KT. So this is actually the spectral width of the light emitting diode. So I have taken so many approximations, so that is why it is 2 KT, but in actual practice, this is 1.5 KT to 3.5 KT. So the spectral width is 2 KT, as I mentioned here, and delta lambda for typical, experimental device. Experimentally, it is found that this delta lambda is between 1.5 KT and 3.5 KT. So now let us find out the value of delta lambda. So we know delta lambda is equal to SC by EPH. This is the wavelength which is generated because of this EPH. And if I sort of differentiate delta lambda with respect to delta EPH, I get delta lambda is equal to minus SC EPH square delta EPH. And if I replace, write in a different fashion, that is delta lambda by lambda is nothing but 2 KT by EPH. So we can get some values of delta lambda for different wavelengths. So if I put lambda is equal to 850 nanometers, I get delta lambda as 30 nanometers. And if I increase the wavelength to 1310 nanometers, then I get 17 nanometers. For 1550, it is about 100. So typical LED gives you, 30, depending on the wavelength, 30 to 100 nanometer. So it's quite high actually for communication. From communication perspective, in optical fiber particularly, it is quite high. So because it will lead to a lot of dispersion, right? Now we have understood about the spectral width. Let us understand about the LED power, how much power is emitted, and also we will try to understand the efficiency part. So let us take first the efficiency. So there are two types of efficiency which is defined. One is internal quantum efficiency, which is defined as number of photons which are generated inside the device divided by total number of electron hole pairs which are generated inside the device. So if number of electron hole pairs are all converted into photons, the efficiency is 1, but that is not the case most of the time. So this is how internal quantum efficiency is defined. External quantum efficiency is actually ratio of number of photons which are emitted out of the device and number of photons which are generated inside the device. So this is called as the external world or external quantum efficiency. So these are the two important parameters. What is your internal quantum efficiency and what is your external? Because ultimately the photons which are generated, they are going outside to either getting coupled to the fiber or traveling to a different destination at some point B. So that is also important. So these two quantities both are important for sources. So let us try to understand these efficiency parameter. So as we know, in a photodiode, in a light emitting diode, there is a P junction, there is an N junction, and there is a depletion region here. So this rate minus dN by dt, because the N is the carrier density, charge carrier density. It is getting depleted. So minus dN by dt is actually proportional to N. This is what is happening inside the LED. And if I solve this, so this N is equal to N0 E minus T by tau, where tau is the average lifetime or against recombination. So N is equal to N0. N0 becomes the initial charge carrier density is E raised to minus T by tau, and tau is the average lifetime against recombination. And if I differentiate this this expression, this becomes dN by dt minus N0 by tau E raised to minus T by tau, and I can replace this with N. So this becomes dN by dt is equal to minus N by tau. So what is the net rate? You are externally supplying the current and there is a depletion happening because of the recombination. So the net rate is externally supplied current plus depletion rate due to the recombination. So externally supplied is J by QD. J is the current density and Q is the charge and D is the width of the depletion region, plus the depletion is happening at the rate of dN by dt. That is the depletion rate due to recombination. So this becomes J plus QD plus dN by dt. And under equilibrium state, steady state, this is 0, and I have replaced here this dN by dt by N minus tau using this expression. So this becomes J minus QD minus N by tau, and net rate will be 0 under a steady state. So this gives me the steady state electron density in the active region when the constant current is flowing across the device, which is given by N is equal to J tau divided by QD. So that was the N and the current part. So now let us see the internal efficiency of the device. The internal efficiency is defined by neta internal. This is how I am designating this. So this is a ratio of radiative recombination rate divided by the total recombination rate. So this is a useful light which is getting generated inside the device. So that is called the internal quantum efficiency. And this can be represented as RR, that is a radiative recombination rate, and total combination, which consists of radiative as well as non-radiative. So it will be RR plus RNR. And this is equal to dN by dt radiative, this is the rate, and divided by dN by dt total, including both radiative as well as non-radiative. So as from earlier expression, dN by dt is equal to minus N by tau, and for radiative it will be minus N by tau R. So this is the average carrier lifetime against radiative recombination. and the dn by dt will be total. So this will be minus n by tau minus n by tau nr. So this can be little simplified here and gets cancelled, and what you get n internal, neta internal, that is efficiency internal, as tau by tau nr. So tau is the actually bulk recombination time. This is the bulk recombination time, and this is the non-radiative recombination time, non-radiative time. Also, we know dn by dt, another expression which will connect tau and tau r and tau nr. So dn by dt total is addition of dn by dt radiative plus dn by dt non-radiative. So this we know minus n by tau is equal to minus n by tau r minus n by tau nr, and this n will get cancelled. So we get a simple equation, 1 by tau is equal to 1 by tau r plus 1 by tau nr. So generally what happens, tau r is equal to tau nr. These two times are same. So if I calculate the efficiency by putting these values of tau r and tau nr in the neta initial expression, I get 0.5 or 50%. That means 50% of the energy is only radiatively emitted. The other part is there is no radiation, it is absorbed or lost in the device. So internal efficiency for a typical diode is of the order of 50%. Let us also try to understand the relationship between the internal efficiency and the power which is generated, that is PINT or P internal. So this is N internal is defined as, neta internal is defined as radiative recombination divided by total recombination, and this is IRR divided by total recombination will be I by Q, and RR, that is a radiative, is the P internal, that is the power generated because of this radiative recombination, divided by h nu. H nu is the photon energy divided by I by Q. So the total becomes P internal into Q divided by I into H into nu. And so the P internal, the power which is generated inside the device, is neta internal into I into h nu divided by Q, and it can be written in a different form. So this is the efficiency part, this is the Planck's constant, this has unit joule second. So while calculating, you should be very careful with the units, and C is in velocity of light, meter per second, lambda is in meters, and Q is a charge in coulomb, and I is the current in amps, and you will get the power in terms of watts. So if you are using MK system of units, these are the units you have to follow. So let us do an example and try to get some idea about the typical values. So if I assume a in-gas phosphide LED which is emitting at say lambda 1310 nanometer, and it has radiative recombination time as 30 and tau nr non-radiative as 100 millisecond. Here it is shown different, but normally these times are similar, and the drive current, which is the I, is 40 milliamperes, and we will try to calculate what is the bulk recombination time, which is nothing but tau, and what is the internal efficiency of the device, and how much power is generated inside the device. So if you put all these values in the expression which I have discussed, what you get tau as 23 nanosecond, what you get efficiency as 0.77, and the power which is generated inside the device is of the order of 29.2 milliwatts. So these are the typical values which are used in optical communication using optical fiber. So now let us try to understand the external quantum efficiency. So for understanding the quantum efficiency, external quantum efficiency, suppose I have this interface. I mean, this is my device and this has some interface. And this is air. So this is say N2. Refractive index here is N2 and inside the device it is N1. This N2 can be anything, but if it is air, then N2 will be 1 actually. So there is an interface, and this is, suppose the photon is generated here, and then there is only certain cone here, and let me put this as angle as phi c. So if your angle is greater than phi c, then the light gets reflected back into the medium. It gets reflected back into the medium, which is not useful. And if your angle is less than phi c, the light is reflected out. What I have shown here is a critical angle where the light is just grazing the interface, so reflected out. Right, so all the light or all the photons which are in this cone only will come out. The other will be reflected back and will be absorbed. So if I put mathematically this is a solid angle where if the photon is confined to this solid angle, only then it is reflected out. So this can be expressed as this part is from the solid angle and the limits are from 0 to phi c, and 4 pi is the total solid angle. So the external efficiency will be integral 0 to phi c 2 pi sine theta into d theta divided by the total solid angle, which is 4 pi. And I can write this sine theta, I can solve this integral and limits from 0 to phi c, and also this gives me half into 1 minus cos phi c, and we know from Snell's law that sine phi c is equal to n2 by n1. The other angle is sine 90, which is 1. So sine phi c can be converted into cos phi c and put in this expression. By putting this expression using cos phi c is equal to root 1 minus n square phi c and doing some approximation here, assuming that phi c is very small, so this half can come here. I get as n external efficiency as this. So this is my n external 1 minus half n2 square by n1 square. So as the outside medium is air, so n2 will be 1, and effectively I will get n external 1 as 1 by 4 n1 square, assuming n2 is equal to 1, and n1 for a typical semiconductor material is 3.6, and if I put this 3.6 value in here, then n external 1 is 0.0193, which is roughly 2%. So the external efficiency, because of the light which is going back to the medium because of the total internal reflection, and only part of the light is coming out of the device, which is about 2% of the light which is generated inside. So this part gives you 2% efficiency. So there is another thing which is happening here at the interface. Not everything which goes here and is inside the solid angle will go out of it. Some part will be reflected back, right? Because the refractive index is changing at the boundary. So even if the light is inside that cone, but when it is trying to come out of the device, there is some part which will be reflected back. So we need to calculate this part also, which will be reflected back. So this is the reflection coefficient. This tau is the reflection coefficient, which is given by n2 minus n1 divided by n2 plus n1 whole square. And we need to find out the transmission coefficient. Transmission coefficient will be 1 minus tau. The transmission coefficient will be 1 minus tau, and if I put this value of tau here and do some calculation, what I get is 4 and 1 and 2 and 1 plus n2 square, and again assuming n2 is equal to 1, I get 0.68. So this is a transmission coefficient, I mean the light which is going out of the device. So n external 2 earlier was n external 1, which we saw was 0.2 or 2%, 0.02 rather, and n external 2 is 0.68. So the total power emitted will be multiplication of these two efficiencies into the power generated inside the device. So if I do this, so basically it comes out to be 0.01, 1%. So only 1% of the light which is generated inside the device is able to come out. So now we will study about the frequency response and bandwidth of the device. So the optical bandwidth, let us first try to understand the optical bandwidth first, and then there's another concept of electrical bandwidth of the device. So we will try to understand the relationship between the optical bandwidth and the electrical bandwidth. So as we know, or you can find in some standard books of optical fiber communication, when you are modulating your source with a light of frequency omega, so as you increase the omega, the power output decreases. So which is given by this expression, P omega is equal to P naught. P0 is actually at DC, power at DC, divided by 1 plus omega square into tau square. Tau is the average lifetime of the photon. So P omega is the power at frequency omega. So if I plot this, so this is, for example, my frequency or omega, and this is the power, say PW. So as the frequency increases, it follows this trend. So this decreases with change in frequency. So what is the how do you define the bandwidth of the device? So where the power has fallen by a factor of half, say somewhere here, say this is 1, this is 0.5, corresponding to this, whatever frequency you get, that is the bandwidth of the device, optical bandwidth of the device. So this is how you define. So this P omega is equal to P naught plus 1 by omega squared tau square. So as we know, this bandwidth depends on this factor tau, which is the bulk recombination time. So for this to happen, P omega, I'm trying to calculate the optical bandwidth. So P omega divided by P0 will be half when this is 3. Then 1 plus 3 is equal to 4. Square root of 4 is 2. So this will be half. So at this point, we will have 3 dB bandwidth. So this can be, so W3 dB will be root 3 by tau, and you can write in terms of frequency, which is root 3 by 2 pi tau. So this is the 3 dB bandwidth, optical bandwidth of the device, root 3 by 2 pi tau. Now let us try to calculate the electrical bandwidth. As we know, the current which is produced in the device, to calculate the electrical bandwidth, actually, see, this is your optical source, and then you have the photodiode, which actually converts this optical energy to electrical energy, and then there is some processing. So the current which is produced in this photodiode as a result of this optical input is proportional to the light falling onto it. So there is a linear relationship. So I omega is proportional to P omega. And electrical power, if I calculate will be I square R, which is this is electrical power, P omega I square omega R. And if I take the ratio of PE omega divided by PE naught, that is electrical power at omega and electrical power as 0, this will be a ratio of I square omega by I square 0. And this can be related to optical power P square omega, P square 0. So as you see, the I and P, they are directly proportional if it is optical bandwidth. And for electrical power, this power is proportional to I square. So this becomes equal to 1 by 1 plus omega tau square. And this will be half when omega tau is equal to 1. So the electrical 3 dB bandwidth is whenever this omega t is equal to half, and by doing the calculation in a similar way, we find out that the 3 dB electrical bandwidth is nothing but 1 by 2 pi tau. One by 2 tau. So if I plot, just to explain you, so this is your omega, and this is how the power is falling with rising omega. So this is the power, or let me now write in terms of current, because that is a quantity which is common there. So let me plot this as I omega I 0. So from the expressions which I have mentioned here, if you take, there will be 2 points, one for the electrical bandwidth, other will be for the optical bandwidth. The optical bandwidth will be somewhere 0.2, and this will be for the electrical bandwidth 0.7, because this becomes 1 by root 2. So this will be 0.7 points, and the corresponding bandwidth is depicted here. So this is the electrical bandwidth. This is the electrical bandwidth, and this is the optical bandwidth. So there is a difference between the electrical bandwidth and the optical bandwidth, and this is how they are related. So earlier I had shown you the expression for earlier I had shown you the expression for electrical bandwidth, and similarly for the optical bandwidth, and this is how it is, the difference is shown in this diagram. So I'll stop at this point, and from next class we will we'll discuss about the laser, and we will try to calculate similar quantities for the laser also. So thank you very much.